Good afternoon to you all, and we welcome all of you to PRAGSAC, which is promoting astronomy in Ghana through school visits and astronomy club, our monthly seminar, virtual seminar that we have introduced, and you are welcome to the April edition. Today, we are privileged to have our brother, Stephen Sottie, MPhil, computer and nuclear science engineer, and also a member of a PRAGSAC team. Stephen has also been very instrumental in the PRAGSAC activities and also in outreach activities as well. This afternoon, he's going to tell us about his work during his MPhil for us to learn more from him as well. And without much ado, I hand over to Stephen to take us through the presentation. And before he starts, I would like to give all of you another special welcome and thank you for joining as well. Mr. Stephen, over to you.
Thank you very much, Albert. I hope you can hear me. So I am so thrilled this afternoon to share with you what I've been doing or what I did during my master's program in the University of Ghana. And to start with, I'll be taking you through some. But before that, in my project, I developed a computational model, or if you want to say a pipeline or an automated system that helps in characterizing mazes at the Ghana Radio Astronomy Observatory. And very soon, some of you might be wondering what mazes are, but I would take some time and then explain what mazes are and why it is important that we study them. So I'll take you through some introduction, the problem that I found at GRAO, what I intend to achieve, and how I intend to do that. And then I'll talk about some discussion, some results that I've had, and then the future works. So to start, Ghana has become a voice in astronomy, or specifically radio astronomy, and for the past 7 years, they've been part of decision making. So on the 24th of August 2017, Ghana was privileged to convert the old redundant telescope at Kotumse into a 32-meter, and happens to be the second in Africa. This state-of-art telescope, or if you want to say it is very, very a special one, because you can, just as you can see, it is being mounted on top of a building, and it's weighing about 50,000 tons. So you can see that the engineering is an awesome one. These 32-meter radio telescopes observe astrophysical sources like such as mazes, which I'll be talking about, pulsars, as well as active galactic nuclei. Now the problem is that astronomical data produced from these measurements are very large. They are really huge. For example, currently, GRA is able to produce 500 megabytes of data per day, and it's expected to reach 20 gigabytes per day when it starts into its full capacity. It is also worth noting that since Ghana is part of the Africa VLBI network and also part of the SKA, which is supposed to be, or is going to be the biggest, if you want to say, technological institutes in the whole world, then you can imagine the amount of data that will be produced even in a day. We are going to enter into petabytes of data, and this data are from astrophysical sources like the maser that I'm talking about. So imagine it's my, yeah, I wish, let me do that. I think, okay, is my screen back? Can you see my face now?
Yes.
Okay, so I
Yes.
wish to explain some things. So let's say this is an angle like the eye view, which maybe you are viewing from, and you project this up into space. You realize that we are going to have these maser sources all in the clouds, and they are really huge in numbers. So it's important that we need to know which is which. And one of the ways by which we do that is understanding their spectral properties. And some of these spectral properties that are of importance are the peak flux, which talks about how bright the source is and at what velocity. Is it was it red shifted or blue shifted? That has to do with whether it is moving away from the observer or moving towards the observer. What's the name? When it is blue shifted, then it means it's getting closer to the observer. And all these things are of importance to us. Also, full width at half maximum, which talks about how narrow or broad the spectral lines are. So you can, to understand this, you can consider maybe when you take a picture, a photograph, when you zoom in or zoom out, that kind of idea gives you what we mean by the full width at half maximum. When it's broader, it means that the image is not too, it's not that sharp. But when it's narrowed, you have, when you have narrowed, when you have sharp images, it means that the full width at half maximum is smaller. That's basically it. And so we need to understand these spectral properties in order to characterize masers. So the aim is to study, of this study is to develop a pipeline or an automated system that will enable us fit maser data and characterize that. And I believe that is going to help even people who are not too good with handling data. The task that the main task of this research is to develop a computational model that will help us estimate those spectral properties that I spoke about. And how do we intend to do that? We want to use a Bayesian Markov chain multi-color approach to fit the model or on the maser data. And with that, we would use the Markov chain multi-color to, it's a model, or it's a model in that will help us determine some uncertainties that are in it. I also intend to develop a web-based data archiving interface for Grau, and that will help us do some queries. Why is this project justified? It is justified because masers, I'll get to masers very soon, but it is important that we know that masers are very, very important astrophysical objects that are bodies that are associated with newly formed massive stars. And they give us indications, or they are actually traces to star forming regions within the interstellar medium. So masers in space. Now, what we know from quantum theory is that when a photon appears on an atom, okay, it leaves there with energy and momentum. And so when we consider the Boltzmann thermal distribution, I don't know if the cursor is able to show that, but you realize that if we have energy levels where E0 or E0 is the lower energy level, followed by E1, E2, you realize that most of the population will be at the lowest or the lower energy level, followed by and then to the E2. Now, I want you to picture this like in a low income country where you realize that if you want to measure that in terms of which people are poor or which people are rich, you realize that most of those who are poor are at the lower we consider them to be at the lower energy level. So just picture that in mind as I explain how masers are being formed in space. And then E2 becomes maybe those who are middle, and then E1 to be those who are in middle, and then E2 to be those who are at the upper. And you realize that most of those people are not like many, they are not bunch. Now masers are just like lasers that we produce on Earth here. It stands for light amplification of stimulated radiation and all that. You realize that masers are the natural version of lasers that happens in the interstellar medium up there in space. And so Ghana Radio Astronomy Observatory telescope is able to measure some of these things. Now, coming back to the diagram here, where I try to explain maser. I was saying that with this system, you have most of the population at E0, followed by E1 and then E2. Now we'll move to the next one. When there is some kind of process which you call population inversion, where maybe based on some pumping conditions, maybe in case for a low-income country, the government decide to pump in some more money, some more cash into the system. Quickly, you realize that most of the people at E0 will go to E1, and so on and so forth. And that is basically what we mean by population inversion. And then when you come to the third one, when you come to the third diagram there, you realize that as some even move to the E3, and then it is important to know that around that level, they can't live longer. It's no, if the conditions are not too good, they might not be able to sustain that. And so they have to move back to E2 or E1. And then in the course of doing that, some energies are being released, as you can see as what's the name, as a photon there. And then the more we have those conditions there, like more seed photons, and then some sources from CMB, and then some more pumping condition, and then we still have that population inversion condition there, then we will keep on producing masers. And these masers are once you are able to set your telescope somewhere at a vantage point, you'll be able to see them. Now, Ghana Radio Astronomy Observatory Telescope has the design such that it has a main reflector and then a sub reflector there. This is just something I'm using too, but I think on the first slide it's really showed that. So we have the source coming to the main reflector. That's the big dish you're having there. And then these are being reflected back to the sub-reflector. So you see a small point over there. And these are being channeled through the feed horn into the server some way, somehow. And through that, we are able to do some data calibration, which is to correct for some instrumental effects, and then band pass correction, which I'll be talking about very soon. And then based on that, we are able to convert this. So these masers that we have are being converted into what we call visibilities, complex visibilities or polarizations, okay, which I'll also talk about very, very soon. To bother you a bit about Grau telescope specification, it is azimuth altitude mount, and it has an elevation range of from 5 to 180 degrees, and then azimuth range of 320. And then, of course, I made mention of the diameter of 32. Then it's able to make observation between 5 to 6.7 gigahertz. The major observation that I'm talking about is at 6.7 gigahertz, and it is right and left circularly polarized. Now, these visibilities that we are talking about are basically, if you want to say, has electrical properties. And these properties are seen as this, as the diagram you are seeing there. So that's the left circularly polarized maser radiation that can be observed at ground. And these are represented by I, Q, V, UV. The I talks about the intensity, how bright this source is. And then the Q carries information about the linear polarization. U talks about the angle in which like the polarization is occurring, and then um, the the V, the circular polarization. And so if you consider equation 1, you realize that it is I squared is equal to Q squared plus U squared plus V squared. And that's what we call the Stokes intensity equation. Now, how were we able to achieve that? Remember, we said we are developing a computational model that will help us characterize this measure. Some also call it statistical model. And we said we are using Bayesian inference. So Bayesian existed around the 17th. He was a Presbyterian preacher who wanted to understand the probability that an event occurs based on some information you have. And so the goal of the Bayesian inference is in this, which we apply here, is to estimate the posterior parts. If you look at equation 2, so this raised that the probability that you want to find out the hidden properties. The hidden properties that I'm talking about are the of the maser. We are talking about the fluid that have maximum, the peak flux, as well as the central velocity, which are in some data D, given the model that we have developed, will be equal to the probability that we have the data and we have those properties in the data, given the model, multiply that by the probability that we have those 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 properties or those spectral properties in the in the in the model all over. What we call the marginal probability is the probability that the data given, or the probability of the data given the model. And if we summarize this, it gives us equation 3, that is the posterior direct proportional to the likelihood. So the likelihood is the probability, this whole thing, and then the prow is this. So it's just like, to make things simpler, it's just like if we want to find out if it will rain. Okay, so the likelihood is the fact that maybe we are in the rainy season, and then the prow is the fact that we are in the rainy season, and then the likelihood is that we have some information about the fact that it will rain. Or maybe the broadcast, the Ghana Meteo has given us some information that there will be rain, or we have some measurement that it will rain. And when you multiply the likelihood times the prow, it gives us the posterior. The posterior. Now, considering the data that we have from GRAO, it has properties of Gaussian. So Gaussian looks like this. If you look at figure A, figure A looks just like a normal distribution, has a normal distribution. All normal distributions have this property. And you realize that Gaussians have certain hidden properties like the mean, the standard deviation. For hello, can you hear me?
Yeah, go ahead. Go ahead,
Okay.
please. Right.
Yeah. So for considering figure A here, you realize that the center or the highest peak or the highest point is located at x equal to what's the name, equal to the mean. Okay, so that's where most of the population. So where the most of the population is, that is where you have the brightness. Okay, and that actually mimics this mazes that we are talking about. And aside having the Gaussian morphology, we have other morphologies based on what I've seen, like the Lorentzian. Okay, and when you multiply from this equation, equation 8, so we have the Lorentzian being represented by equation 7. Okay, and all of them you realize that have some hidden properties, like you see the x here can be seen here, and then there is some scaling parameter which tell us how the distribution spread from the mean, and of course it's giving us hints back to the full weight at half maximum. Okay, and then if you look at the void probability distribution, which can be obtained by a convolution between the Gaussian and then the Lorentz-Cauchy, when you combine them together through a process called convolution, you can get a void distribution. And so if you look at the profile at B, the profiles at B, you realize that Gaussian is being represented by the red. Okay, and you realize that it moves along the x and then picks up and then come back to the x again. If you look at the Lorentzian, which is depicting the blue, it's a bit more narrowed, and then the void is also, which is green, is a bit like broader. And if you visualize the ground data or the maser, you realize that all these morphologies can be seen in some of them, okay, which I'll be showing you very, very soon. Now, back to this. You remember back in high school when we want to find the maximum part of a curve, you realize that you have to take a differentiation, dy dx of that, and then that gives us that. And that can be seen in, is it equation 6? Okay, and that is what we call what's the name, using the likelihood. So the likelihood we are talking about through computation can be seen at equation 6. So equation 6 gives us that computation. But then equation 6 cannot be solved. It can be solved, but it's quite difficult to solve because it gives you some logarithmic equation. And so that is why it's important that we bring in the Bayesian thing. So here I wrote that the maximum likelihood assessment technique, which could be used to get these parameters that these hidden properties based on the morphology that we are looking at, it will be a bit difficult, it will be laborious. So we need to introduce what we call the Bayes approach. And that helps us get a full posterior distribution, which explicitly captures the uncertainties in the parameter. Now, another advantage that the Bayesian have over is that it helps us to do some model comparison and selection. You realize that right now I'm bringing together two models, the Gaussian, Lorentzian, and then the void. I'm bringing in, and at every point in time, you need to do some optimization, some model selection, and then comparison. And the Bayesian inference approach also helps us do that. But the ML, which is the maximum likelihood, it's not able to do that. And then furthermore, it can also help us find out some missing data. Sometimes you take data and then based on certain property conditions, there are missing values and all that. With a Bayesian approach, we can actually harness that. Now, quickly, I spoke about data. So I'll use the result to explain the data processing. Now you realize that in data processing, we call something noise. So up there in space, we are being challenged with some stuff like the clouds, which imagine you are standing here and then you are taking picture like far away, standing on Earth, and then you are taking picture far away. You realize that the clouds will be distracting or will be obscuring your ability to capture that. And so in order to do that, in taking measurement at ground, you need to do what we call on source and then off source measurement. So with the off source is done is just you just move the telescope to a particular source, unknown one, a known one, which is like an off source. So, sorry, an unknown one, and then just capture the data from there, which you call the off source. And then we move the telescope to a source that you know, and then you capture it. And by comparison, you realize that we are having the off source being some signal rising from maybe somewhere, maybe 120 up there. Now the plot you have there is the flux, a plot of the flux density against the velocity of the sky velocity. And if you look at the on source, you would see some spiking. So there's a spike around the velocity, center velocity at with a center velocity around 0.03 kilometers per second, and then a higher peak around maybe 998.920 Jansky. Another importance of developing this model is actually to work against the already tradition of using eye. So normally they just use the eye to gauge they visualize the data and then use the eye to gauge. But with this model, the model is able to print out every information that you need to know about this about a particular source, and I will show that to you. So there are a number of major sources which we observe, and one of them is the G962. For this study, I just for this presentation, I'm just using 3 of them, but one of them, which is the simplest, which is also very popular, is the G962. And this is how it looks like. You see the morphology looking like that of a Gaussian. If you spread it bigger, you realize that it's showing some Gaussian and then its families, like the Lorentzian and then the void, just as you can see there. And we are saying that the spectral distribution of this maser has been corrected. So how do we correct that? We correct that by subtracting the off source from the on source, and that gives you the subtracted, as you can see on the third diagram figure there. So you realize that it actually moves it down to 0 at the flux density, 0 Jansky there, and with that you can do further processing. If we consider the next one, we also repeated the same thing for that, and you see it peaks around 5, its peak flux around 571.211 Jansky, also around 0.029 kilometers per second around this point. And you can see that because owing to the fact that the center velocity is positive, it means that it is blue shifted, meaning that it is moving towards the observer, or it's moving away from the galactic center towards the observer. Then there is one phenomenal one, which is the G339, which has about 7 flares, 7 flares. And then you realize that the peak is around 283.296 Jansky. Now the model that we've developed, or the model that have been developed, is supposed to quickly pick each peak. So realize that with diagram 1 here, there are 2 peaks, but I mean it's able to only pick just the one. And then with the gene 351 having 5 peaks, it's able to just as you can see from the dotted line there, I just use the dotted line to just mimic those positions, and it's been able to pick I think 4 or 5 out of, yeah. And then with the gene 339, it's able to pick quite a number of them: 1, 2, 3, 4, 5, 6. Normally we ignore the list flags because they are not really of importance to us. What we need is the pick flags. And then we also went on to fit on our Gaussian model on the maze at the spectrum that we have, and you realize that it's been able to mimic almost all of them. With the G9, with the blue being the original data that we had, you realize that G1 showing red is Gaussian, has mimicked it, like it's Gaussian, if you want to say Gaussian mimicked, and then G2 as well. And then it's been able to estimate the hidden properties, which is the mean. And then the mean there gives us information about the center velocity. Already, this gave us the peak flux or the brightness. This is giving us the center velocities. Then we went ahead to do some model, some predictions on it using the RMSE, which tells us how the estimated or the observed align with the predicted. And realize that it is that huge. Okay, we are expecting something between 0, maybe something like lower, closer to 0, but it is that huge, which I'm still trying to find ways to maybe correct that. Maybe there are some hidden things in the data that I have to correct. But then if you look at the R squared, which tells us how the dependencies of the variables on one another, you realize that it is close to 1, which is very, very good. If you look at the G351, you realize that the RMSE here is very good, which is 0.4182, and then which is the residual. And then the R squared here is also approaching 1, which is also really very good model. Then the one that does best when it comes to RMSE is the G339, which is 0.3280, and then has maybe the least R squared there. Now, the model is able to, you can see that this is a tabulated result from the estimations on the spectral characteristics of the maser sources that we spoke about. And you can see that the model is able to print out all information about, in terms of the flags. You realize that G962 had 2 flags, has 2 peaks, okay, represented here. The least being 156.350 Janskis, and then the highest being 998.8.920, and so on and so forth. It is giving us all the information that we wanted. Remember, we are looking for the flags, the the center velocities, and then the full width at half maximum. And then we are able to get information on the model performance matrices. And you realize that from the information we explained earlier on, the RMSE, the G9, the G339 is doing far better than the three sources that I spoke about. With the R squared, we have G9.62 doing far better. Then we also have the chi squared also being represented, the reduced chi-squared, and then AIC, and then BIC, which is the Akai-K inference criterion. With the Akai-K and then the Bayesian criterions, you realize that if you have a lower one, a lower value, then that one has a best prediction. And so you can see that from all indication that the G9.62 has a far better prediction than the others. Then we went on to do some corner plots. I hope you can see the screen. It's not too visible, but that is also a way to tell some how well the model performed. And you realize that the uncertainties, there are no much uncertainties in the data. If you zoom, if you look at the diagonals, the histograms are along the diagonals, you realize that the amplitude here, which is 0.886, does not, considering the G9, it's not too far away from that. And then when we consider the central velocity, the center there, which is 0.03, is also not too far away from what we already have. Now, conclusion. The conclusions are that the model has a more convenient way of estimating the spectral characteristics of Grau Mesa against the eye gauge. I made it clear earlier on that over the years, one of the ways they are able to do measurement of the spectral properties of mesas at Grau has been maybe using eye gauging. But the model currently, once you all you need to know is to just copy the data and then put it into the model, and then it just print out every information that you have. Just run it, and then it just print out every information that you need. And then the model has also been able to estimate and display the model properties as well as their corresponding data properties. So the model properties for each one has been established. Remember, we are able to get the central velocity from the mean of the model. So the model's mean is giving us the central velocity. The peak or the brightness is being given by the amplitude, if you want to say, and then the full width at half maximum is being given by the variance, how the spectral line moves away from the center. And then the model is also able to mimic all the peaks, okay, as compared to the previous. Normally, the astronomers, what I know, or per literature, all that I've seen so far, they only focus on just one peak. But currently, the model is able to pick maybe no matter the number, 2 peaks, 3 peaks, and even up to 7 peaks. It's all able to pick all that. All you need to know is to just adjust the what's the name, the parameters. And then I also found out that as the number of flares increases, the flux intensities decreases. So you realize that G9 from here, G9 has just 2 peaks, and then it is what's the name, 998.92. That's the highest. But for G51, which has about 5 peaks, reduced to 571.211, and then G339 also reducing to 120. So That is it. And then the model is also able to mimic all the peaks comparatively to just mimicking one. I've already established that. And then I also established the fact that the fact that maser velocities were also sorted into positive and negative. You realize that some of the velocities were negative, some were positive. The positive indicating that it is blue shifted, and then the negative showing that they are what's the name, red shifted. So that's by the way how we are able to tell that a maser source is blue shifted or the is blue shifted or is moving away from us or is moving towards us. And the next thing I'm working on is to feed this this onto a web-based archive, so that maybe no matter where you are, wherever you are, if you are in Europe, or you can just be able to access data far away of data from Ghana, far away from there. So that is the stage I am right now. These are some references, and then so thank you. Maybe if there are some questions you want to ask.
Thank you, thank you, thank you, thank you. Thank you so much, Stephen. And
You're welcome.
that was very exciting. And I might say that it has been explained to the layman's language. Even those of us are still doing astronomy. Some of the things about masers and so on look as if they are still far away from us. That shows that astronomy has a very broad field. And thank you for breaking them down into the understanding of everyone.
You're
So
welcome.
the platform is open for questions now and comments. So just raise up your hand, then I'll call you. Oh, okay, if you
I have a question.
Godwin, yeah,
Yes.
Go ahead, Godwin.
Yeah, Sottie, thanks for the very beautiful talk. At least I've learned a lot.
You're welcome.
So I have a couple of questions.
Okay.
I'm just curious about your hardware. So you took the data from the observatory, the telescopes in Ghana, right?
Yeah.
So at what frequencies are you observing?
Between 5 and so this is basically 6.7, but Grau has some range between 5 and a 6.7, but the observation
What? Gigahertz or megahertz?
Gigahertz. Yeah.
Which means you are basically sampling at 2 times that frequency.
Yeah.
Wow, that's a lot of hardware. Yeah. Anyway, so you did mention something about a full width half maximum of these masers. So how exactly did you measure that? Did you get that from your maximum likelihood method, or how do you do that?
So from the Bayesian, you remember I made mention of the fact that the maximum likelihood will be able to do that. It's also able to do that, but it gives you some logarithmic what's the name equation, which we can't solve just like, and so that is where the Bayesian approach comes in. So a Python code was written to get that.
Okay. The reason I ask this question is,
or you want to find out on the equation?
No. So I have one question regarding that. So the full width half maximum, right? Is it frequency dependent?
Yeah, it's frequency dependent, and keeping a frequency of 6.7 gigahertz.
Okay, so it's not like an integrated flux. You calculate this at a particular frequency.
At a particular frequency, because the measurement was at that very frequency.
Okay. Yeah. Okay. So the flux that you did mention is not an integrated flux over frequency. No. It's in one frequency band.
Yeah, in one frequency band.
Yeah. Okay. Now, if you go to slide 24, I have a question on the slide. Yeah. So I think that's okay. Yeah.
That's okay.
So you did this measurement and then you compare it to your model, right?
Yeah.
And then you code this value as r squared. I don't know. I mean,
Yes.
if my memory sets me right, the r squared it used to probe the linear relationship between two variables,
Yeah. The
So I
dependencies.
think, yes, I think the best way to do this is the chi-squared, which I think you already mentioned, because this clearly is not a linear relationship. So I think a goodness of fit like chi-squared or reduced chi-squared should be enough. I don't think r squared is a good way to
Okay.
do this.
Okay.
Um,
Okay.
yeah,
Very well. Okay. Noted.
okay,
Thank you.
yeah. And then one last question before you
Okay.
continue. So um, so how do you tell if the maser is pointing away from us or pointing our direction?
Pointing away from us or pointing in our direction. So
Yeah.
it is by the charges, what are the signs on them,
So you use the
on the
Stokes
center.
parameters basically.
Yeah. So the Stokes parameters. So like I made mention, if you
Mm.
look at the gene, considering the gene 339
Mm-hmm.
on this, per the calculation of the Stokes parameters or the visibilities that we've done, you realize that it's giving us negatives, some negatives. So the negative is an indication that the negative the highest peak, okay, or the highest brightness at the being located at the negative velocity shows us that it is moving away from us.
Yeah, so this is the source moving away. So the
Exactly.
polarization should tell you whether it's polarized in our direction. And I think this you get
Exactly.
from the Stokes parameters.
Yeah.
Okay.
Yeah.
Now, also from this plot,
Mm.
so how far, so when you are looking at these mazes, I mean, how far can you, I mean, how far can you look, at these frequencies?
How far? So we can get that from, I mean, the equation. I've not really done that, but from the frequency relating wavelength kind of thing, equation, keeping the velocity constant. I've not done that actually. Yeah. How far we can look, I've not done that.
Yeah, so at these frequencies, do you guys worry about dispersions? Like atmospheric dispersions or dispersions in the interstellar medium?
Yeah, so that is where the subtraction thing. So
No, the
the
subtraction thing is for noise reduction, this I get.
yes, but the system has been designed to actually take care of all those things, all the odds. The systems in there takes care of all that. I um, actually ask for those things. I am not, how do I put it? No more of a, as at that time, I wasn't that much inclined into the astronomy thing as at that time. But so finding out that they made me understand that the system there has a way of fine tuning all those things that might.
So when you did your Monte Carlo, did you
Yeah.
factor all this into it, like the effect of dispersion on your signal and stuff like that?
No, I didn't do that. All the only thing I did was the band pass correction thing.
Oh, okay. But how did you apply your bandpass? Just curious. You just move into frequency and you chop off the frequencies you don't need, or how do you do that?
Yeah, so you just chop them off.
Okay.
Yeah.
And then this didn't introduce any artifact in your signal.
No.
Okay. Okay. And that's all. Thank you.
Thank you,
Thank
Godwin.
you. Thank you so much. Yes, thank you. Any other question and comments? Any other questions?
Yeah, I have one last question if I can ask.
Okay. That's very good.
So the source that you did mention here, how far is this source from us?
Yeah, so that's the one I was saying that I couldn't. That aspect I've not looked at. Yeah.
Yeah, but is
I
it
only.
is this within our galaxy or
Oh, okay. Oh, it's within. They are
it's
all
within our
within.
galaxy?
Yeah, they are within our galaxies. Yeah.
Okay.
Because of the gene. So the gene, there are other sources. Okay, so I only concentrated on our galaxy. So that's the gene.
Okay.
Yeah, the gene there.
Okay. That's actually the reason I asked the earlier question about at these frequencies, can you observe
Okay.
extragalactic sources? Because at these frequencies, then they get absorbed in the interstellar medium or something. I don't know. Or they get blocked by other objects, and so you probably are not able to see them.
Yeah.
Mm.
It makes a lot of sense.
Good.
Okay.
Okay, thanks. Yeah. Any other question? Yes, yeah. Jifa, yes.
Hello.
Hi, Jifa.
Yes, Jifa, yes.
Hi, Steve. How are you?
Yeah, I'm good. Good to hear from you, man.
Thank you very much for your nice presentation.
Thank you, Jifa, for joining.
Really, it's nice. I'm too late to. I got the link from WhatsApp group.
Okay.
Yeah, I'm working also on the same work with you, one of the projects
Okay.
that I submitted last week. But this nice work will communicate, especially through WhatsApp. I communicate with you. I need your work.
Okay. Okay.
Nice work.
Okay, sure.
Thank you very much.
Sure. Yeah.
Yeah, great, wonderful. Jifa, thanks for coming all the way from Ethiopia. We are grateful for joining.
Thank you.
Yambo, we also thank you also for joining from Namibia.
Hey, Emilia.
We have I think somebody from Egypt, right? As well. Okay. Yeah, any other question? Any other question?
Yes, I have a question. Because Sottie, do you by any chance have the frequency spectrum of some of these sources?
Maybe I have to check that. Maybe kindly connect maybe backstage whilst I find out that. Yeah.
Okay.
Yeah.
Yeah, because I want to know about what frequency range we can observe the sources. Even can we even observe at below sub-megahertz level frequencies, like a few megahertz frequency?
I think maybe that has to do with where you are positioned, possibly. So that's one of them, where you are positioned. But then considering Grau has the range between 5 and then 6.7. And then there are quite a number that we are able to observe currently. Yeah. But like I said, I would maybe you connect to me backstage whilst I do some.
I don't think you understand my question.
Okay.
I mean, so okay, yeah, we can talk about this backstage. Yeah, sure.
Okay.
Yeah, I think that's the best idea, so that more can be learned also from there. Yeah. So yes, we thank you so much for the question sessions.